In this video, we're going to look at the process of weathering rocks and how rocks are broken down. So we spend a lot of time talking about how rocks are made, but really that's only one part of the rock cycle. So if we look here at the diagram, we've talked about igneous rocks. So igneous rocks either form deep underground as plutonic rocks, or they form at the surface as volcanic rocks. But once they're at the surface, things start to change and we start to weather those things. So why in the world do rocks weather in the first place? Why do they fall apart? Why don't they sit there? They're rocks. They're hard, right? Well, let's think about this environment. You probably recognize Camelback Mountain. What's Camelback made of? What is the geology there? Well, the head of it, over on the left, is actually called the Camel's Head Formation. And those are breccias and sandstones and conglomerates that were formed in an alluvial fan that streamed off of the McDowell Mountains. We're going to talk about sedimentary rocks coming up, and we'll talk about what those all terms mean. But let's focus on the hump of Camelback. The hump is made of granite, actually very old granite. Where does granite form? Alright, hopefully you've thought about it for a second there, and you realize that granite is an intrusive igneous rock, which means it forms underground. So when granite forms, it's nice and warm, and it's cozy, and there's lots of pressure pushing on it, so it's all like swaddled up inside the earth and nice and happy. What's going on here? What's sitting in the middle of Phoenix? There's not a lot of pressure. It's really cold. At least compared to where it used to be. It is Phoenix after all, right? But it's cold and there's nothing pushing down on it and everything is so different. So it starts to change. So the weathering happens because of a change in environment. So what the rocks are going to do, the rocks and the minerals start to change to a different form that's more stable at these new environmental conditions that it's in. So let's look at how this happens. There's two major types of weathering. It's either mechanical or chemical weathering. Alright, so mechanical weathering breaks rocks into smaller pieces, and chemical weathering actually changes the chemical makeup of the rocks. So here's a lovely photo for you of a rock that is being weathered. Which one is happening here? Well, hopefully you can recognize that the rock's breaking into pieces, right? There's big cracks in it. So we know obviously mechanical weathering is going on. And if you look in the background, I see lots of snow, so that's probably one of the major contributing factors is the weather here. But that's not all. If you look closely, particularly around the bottom of the rock, it's kind of brown on the outside, right? That means the rock is rusting. That's actually a chemical change. So it's not just one or the other here. You actually have mechanical and chemical weathering going on. So we're going to look at chemical weathering first. The key to this is the rocks are broken into smaller pieces. That's the only thing that changes is the size of the rocks. Right? This is known as either physical or mechanical weathering. So you may hear both of those terms. But there's absolutely no change in chemistry. Now there's 5 important processes here, some more so than others, but we're going to go through each one of these really quick just so you can see why this happens and where it happens and what it looks like. So first we have frost wedging or frost action. Now this occurs because of water. So here's a rock on the left. It's a granite. You can tell that because it's light in color. And there's a crack in that granite. And one day it rains. And that crack fills up with water. There it is. But overnight it gets cold. And what happens when water gets cold? It starts to freeze. Now, what happens to water when you freeze it? If you put a bottle of Dr. Pepper in the freezer because you need to get it cold real fast, and you forget about it and leave it there, you're going to come back to an exploded bottle, right? Because water expands as it freezes. So night comes, that water freezes, it expands, and it opens that crack up just a little bit. But during the day, that water melts, and then it refreezes again the next night. And then it melts, and it refreezes again the next night. and it melts and it refreezes again the next night until finally it freezes just enough that that rock falls off. Alright, so this is a really common reason for rock falls, is this frost wedging. And so as that rock falls off, you've got a big angular piece that falls to the ground. And I'll show you just what that looks like just here in a second. But the key to this happening is you need warm enough temperatures in the day to melt the ice and cold enough temperatures at night to freeze it. That's where this is going to happen the most. So when those rocks fall down to the bottom of the cliff, they make these big piles. And this right here, that slope there, that's called a talus or a talus slope. And those are all sorts of angular pieces that have popped off the cliff thanks to that frost wedging. When we look at breccias in sedimentary rocks, this is one of the ways you can make a breccia, actually, is the pieces from this talus slope. Now we can do this, we can also weather rocks by growing crystals of other minerals, not just ice. So for instance, salt crystals. As salt crystals grow, they expand, take up space, and then it breaks the rock. It's sort of interesting because in this case, once it breaks the rock, you can get like those crystals get blown around thanks to the wind, and little pebbles get in, and those little holes get bigger and bigger. So this is often called either honeycomb weathering or taphoning. So those are common words you may hear too. So this is going to happen most often either in hot environments where water evaporates quickly because you need salt water to get on the rock, but then the water evaporates so the crystal can grow. Or it can happen in marine or shoreline environments where you have a ready supply of salt water. So let's think about this. Where are some places other than, I'm not sure where the picture on the left is. The picture on the right is a churchyard somewhere in Great Britain. You can see some taphonia even working there on the gravestone. But do we have anywhere close to us here in Mesa where you have big holes in the rocks? Like a hole in the rock? What about Papago Park? Papago Park has these big, beautiful holes. This is actually an example of taphonia on a really nice big scale, which is pretty cool. Alright, one more here. This is called unloading. So unloading occurs in plutonic igneous rocks. Right? Now if you remember, plutonic igneous rocks are ones that form deep underground that cool slowly, have big crystals in the rocks. And so these are buried under lithostatic pressure. So lithostatic, lith means rock, so it's the pressure of the rocks pushing down on it. But once these are exposed to the surface, that pressure is reduced off of it, and the rocks actually start to expand. And when it does, you get this process called sheeting. It actually peels off in flat sheets. This can also be called onion skin weathering, which is pretty cool. This is really, really important for areas that you have lots of granites and diorites, so like a batholith or a stalk or a laccolith. You'll often find this happening. Now, speaking of batholiths, the Sierra Nevada in California, the big mountain range that runs down kind of the eastern side of California, is covered in granite. So this is a video from Twain Hart Lake, just outside of Yosemite National Park. So what you just saw here is actually unloading in action. This is a very cool video because this is not usually caught on camera like this, which is pretty awesome. But you can see this nice, beautiful, round shape of the granites here. We're going to look at what that's called here in just a second. But, yeah, but does the rocks expanding when you release the pressure. Now, I've heard in granite quarries that sometimes after they blast and pull off layers of granite, that the rocks behind that are now exposed will actually explode like this, even just because of that happening, which is kind of cool there. Now that round shape, this is what we call an exfoliation dome. Exfoliation domes are, because of unloading, because it's peeled off into thin sheets coming off of here. This particular one is my very favorite exfoliation dome, mainly because it is in the great state of Texas. So this is a place called Enchanted Rock. And you can see this pretty pink color. It's because it's a granite that's really enriched in potassium feldspar. It's called the Town Mountain Granite. This is actually the stone that the Texas State Capitol building is built from. So if you ever visit Austin and visit the State Capitol building, it's actually this pink color, which is kind of cool. Here's a couple other views of that here on the left, which you can see where these little pieces are actually popping off and then they slide down. On the right is another example of a famous exfoliation dome. This is Half Dome in Yosemite National Park. Now this used to be a whole dome, but thanks to glacial activity throughout this area, you have a really big U-shaped glacial valley. That's Yosemite Valley, was where a huge glacier used to be. So this thing was actually completely full of ice at one point, and it actually weathered away that other half of Half Dome. But this is a pretty famous place. It is one of the, I think it is, from what I understand, it is the highest or the tallest single extent to rock climb in the entire world. So if you're a rock climber, from what I understand, this is kind of a big one to go do. Either Half Dome or El Capitan there in Yellowstone or in Yosemite National Park. All right. Just a couple more of these. We have thermal expansion. So you get volume changes when rocks are heated and cooled. When any material is heated and cooled. When we've talked about how to melt a rock, as rocks get hot, in order to melt, they have to expand quite a bit. But even just heating them makes them expand. Because that heat is basically you're vibrating the atoms. And as they vibrate, they take up more space. So they expand just a little bit when you heat them. And then when it cools down, they contract back down. So this happens in places either during extreme heat events like forest fires that blow through, or in deserts or arid environments where you have really where you have temperatures that change drastically between night and day. So you're looking at over 30 to 40 degree differences between night and day. Now this isn't a very important factor. It doesn't happen very easily, and actually probably is partially a chemical reaction because it happens a lot faster when there's water in the rocks mixed in there too. But there are places like this picture from the desert where rocks have just fallen apart. And the last of our mechanical weathering processes is biologic activity. This occurs due to plants and animals. Now plants are particularly effective at this because of those roots systems that they have. So when the roots grow, they can actually go in between layers of rock and break them up. This is called root wedging. And just how determined these roots of trees are, this is why you don't want trees near your foundation of your house or near roads or near sidewalks, because they can move them around too. Now out of all of the animals in the world, there's one animal that's really, really, really efficient at breaking up rocks on a really big scale too. Do you know what that animal is? It's you. Humans. Humans do most of the mechanical weathering in terms of biologic activity, I feel like. On the left here is a picture of an open pit copper mine, and how they mine that is they blow those rocks into little bitty pieces and then truck it out. And every time we do that, that is just mechanical weathering. The picture on the right here shows you some trees and lichens that are breaking the rocks up, so they do it a lot too. And even ants. Ants are actually pretty good at this, but humans tend to move things around a whole lot faster. All right, now if we look at the other side, if we look at chemical weathering, chemical weathering refers to the many chemical reactions that alter or destroy minerals and the mineral chemistries when a rock comes in contact with water, solutions, or air. In all of these things, water is the single most important agent. Water is involved in every single one of these. And actually in a whole lot of those mechanical ones too, if you sit and think about it. So water is really, really important here, and I'll show you how each one of these uses it. All right, so first, dissolution. If you take a scoop of salt and dump it in a glass of water, it dissolves. So dissolution is, it occurs because mineral bonds are broken by the water. If you can see the little diagram here, those water molecules actually get in between the sodium and the chlorine atoms and break them apart and hold them away from each other. So the mineral halite is able to dissolve in just pure water. And when this happens, the results of this dissolution is ions in the water. And we talked about ions a little bit before. Those are charged particles. Now some minerals need a little bit of help to dissolve, like calcite. So this is a little image of calcite reacting with hydrochloric acid. And that calcite is in a rock called limestone. You can see it bubbling away. Now this speeds up the process quite a bit, but you can actually find weak acids naturally in the environment. All right, so the weak acid that'll do this is called carbonic acid. All right, carbonic acid is H2CO3. You can see that in here. CO3 is calcite, so calcite plus carbonic acid is going to give you ions, and this is called a salt. It's a chemical salt, not a salty salt, but it's a salt in chemistry. So what happens here is you have calcite. We add a little bit of carbonic acid. This is naturally occurring in rainwater. Rainwater is actually naturally slightly acidic, and it's because of a reaction between the water and the carbon dioxide in our atmosphere. Now when it does that, it creates what's called karst landscapes. Or, if you're into it, it causes caves and caverns. And that's because this carbonic acid gets down into limestone and dissolves the limestones out and you form caves. Right, so some caves around here where this has happened, at least in Arizona, we've got karst caverns. That is down kind of near Benson, not too far from Tombstone, just in the Whetstone Mountains. And this is a picture from Karst. If you've never been there, it's a beautiful cave system. I highly, highly recommend it. We'll look at them a little bit more when we talk about groundwater. I'll put a little bat because there's actually lots of little bats that live there. It also creates sinkholes, and Montezuma's well is an example of a sinkhole. This is up north in the Verde Valley. And this happens when basically a cave collapses. So the very top of the cave collapses in, and it leaves these big sinkholes behind. But again, we're going to look more at these more in when we talk about groundwater, but I thought it was worth noting now. All right, hydrolysis is a process that breaks down silicate minerals due to a reaction with water. If you remember, silicate minerals make up 90% of our minerals, and most of the minerals in the continental crust, and almost every single bit of the oceanic crust. So these are really important minerals, so this is a pretty big process. So what we're looking at here, the left is potassium feldspar. That's one of our Bowen's reaction series minerals. We're going to add a little bit of acid to speed up the process. It always helps. And we're going to add water, because water is the most important thing here, right? What you end up with is getting the mineral kaolinite. Kaolinite's a pretty important clay mineral. It's used industrially quite a bit. So the results of hydrolysis, what you get out of it, are going to be clay minerals like kaolinite, ions like the free potassium here, and silica. Now this result here, these products of weathering, are going to be really important when we talk about sedimentary rocks. So keep these in mind. Now quartz is a silicate mineral, but keep in mind that quartz is very very hard to chemically weather. It doesn't break down very easily at all. And the picture here is a bunch of sand dunes, because those are all tiny pieces of quartz that won't chemically weather. Alright, oxidation. Oxidation is going to transform iron-bearing minerals into rust. So what you see here is a couple examples. On the left are some rusty cans you're used to seeing. And on the right, this is actually a granite. And in this granite are big crystals of biotites. And you can see around those biotites, there's actually little rust rings where they have rusted. Right? Now, iron-bearing minerals aren't the only things that oxidize, but it's one of the more common ones we see. Minerals like malachite and azurite are actually from the oxidation of copper-bearing rocks. So when iron rusts, it turns into like this red, brown, orange color. But when copper rusts, it turns green and blue. Alright, so your product of oxidation, for the most part, is going to be the mineral hematite, which is red, or the mineral limonite, which is yellow. So this is actually a what's called a pseudomorph. So pseudo is false and morph is shape. This used to be a pyrite crystal, which is an iron sulfide, but it's been replaced by limonite, but it still has that shape of pyrite, which is awesome. Here's some red quartz that's coated in hematite because everything else is weathered away, and you've got that the quartz left over. But the hematite is from those iron-bearing minerals that were. These are pretty common right now. Hematite-bearing quartz from Mexico is really big on the mineral markets. I keep seeing those. And here's some quartz coated in limonite. You can see the difference in color there, which is pretty cool. Alright, so this is a little table that kind of puts it all together. I told you the products of weathering are going to be really important. But if you look, lots of silica, lots of ions, and again, some clay minerals thrown in there too, which is important. Like I said, when we talk about sedimentary rocks, we're going to look at where these come to play in sedimentary rocks. Alright, so we talk about these two processes kind of as separate entities, but they really don't. The two types of weathering do not act independently. They work together. In fact, mechanical weathering actually speeds up chemical weathering because it creates more surface area to attack. And that's what this picture says. If you have one big rock, it's got like a surface area of 6 square meters. But if you break it up into smaller pieces, now there's 24 square meters that you could put water on and start to chemically weather. So that speeds that up. But chemical weathering speeds up mechanical weathering because as it breaks down minerals, especially when it breaks down some minerals faster than others, it creates weaknesses, and it makes it a lot easier for those rocks to break apart later. So they help each other out a lot. Here's an example of one of those. This is called spheroidal weathering. You start out with cracks in the rock, and those cracks are planes of weakness, so water is able to get down into those and start chemically weathering them. And over time what happens is those rocks get kind of rounded off, and then they get even more round until eventually you get rocks that are actually very round. If you notice, these rocks have a little bit of a pink tinge to them from potassium feldspar. So granite in particular tends to undergo spheroidal weathering. It's a great word, isn't it? So where can we find rounded boulders of granite that's around here? About the top of Camelback. That's how we started this, was talking about the granites of Camelback Mountain. And if you look, all those rocks at the very top are actually kind of rounded off. Look at all those tired hikers. Where else? Well, some other places include Texas Canyon. This is on Interstate 10 on your way kind of east or south into New Mexico. And on the right is the Prescott Granite Dells. The lakes around there go actually through the Granite Dells. They're quite lovely. Now we've talked a little bit about when this happens, but there's things that either speed up or slow down how quickly weathering happens. So the factors that are going to affect the speed of weathering the most is going to be rock type and climate. Alright, so for instance, these headstones are both from 1868. Right? They're in the same graveyard, which means they have the exact same climate, the exact same weather all the time. You can see the nice green grass, so it's obviously not here in Arizona. But Mr. Peter Sweat, there on the left, has been remembered in perpetuity a lot easier than whoever this guy is on the right. I basically see the word died. Looks like maybe February 29th. And we know it's 1868 when he died. Alright, so what's the difference between these two? If they're in the same place, they look a lot alike, right? Well, Mr. Peter Sweat's family chose a granite headstone for him. Or the other guy, it's using limestone. And limestone has calcite, which tends to weather a little bit faster, particularly when it's wet. If you have an environment that gets more rain, because rainwater has carbonic acid in it. Alright, but if you have just a bunch of igneous rocks, what's going to weather fastest? So the minerals at the top of Bowen's reaction series are more comfortable at high temperatures. So they weather easily. So olivine, it is not happy right at the surface of the earth. So it tends to fall apart. And it's really hard to find olivine sitting around. Where the bottom of Bowen's reaction series, these are used to low temperatures, so they tend to be a lot more stable, like quartz, right? But it's not just the so quartz is really hard to chemically weather. Did I say that already? This looks familiar. Well, the other parts of this is the structures. So the simple structures you find at the top of Bowen's reaction series, like the isolated silicates or the single or double chain, those are pretty easy to break apart because you don't have bonds that hold them together well. Versus the sheet silicates or the framework silicates, like the micas or the quartz and feldspars, those are going to be a lot harder and a lot harder to mess with because of those more complex structures. Now, but like I said, one of the biggest things going to affect this is going to be the climate. So a climate that's warm and that's humid has the fastest rates of chemical weathering. Alright, so somewhere like Florida is going to have super high rates of chemical weathering versus Arizona that's really dry, or even Canada that's really cold. Those are places that aren't going to have just a whole lot of chemical weathering going on. Now, one kind of interesting look at how rocks weather differently, it's called differential erosion. So weathering is just breaking the rocks down. Erosion is actually where something picks up the rock and carries them away. A lot of times that's either wind or water. And these are two examples that we looked at in class on plutonic processes and plutonic forms. You have shiprock here with that beautiful dike coming off of it, and this was a dike in Colorado. In both of these cases, they used to have rocks surrounding them. But the rocks that surrounded them were more easily weathered and eroded, so they've all been carried away and the dikes are left behind. Other examples of this is the Grand Canyon. There are rocks in here that will weather pretty easily and erode pretty easily, and there's rocks that don't. For instance, the red wall limestone is one of the hardest extents of the canyon hike. It's 400-foot sheer cliff of limestone. Normally limestone weathers pretty fast because of acid and rain. But this is Arizona, where we don't have just a whole lot of rain. So that limestone is actually pretty strong. If we go on down, you actually have some igneous and metamorphic rocks that weather very slowly too. And so those rocks in the inner gorge tend to form really steep cliffs. Or the mittens. This is in Monument Valley. The top is a nice hard Cayenta sandstone. And that hard sandstone weathers pretty slow, so it actually protects the stuff under it, which weathers a whole lot faster. And one last look. We have Bryce Canyon up in Utah. So these are hoodoos. That's the little goblin shapes. Looks like little people standing there. Those are called hoodoos. And if you look at the top of the hoodoos are they're capped in like this kind of funny rock. It almost looks like concrete on top, doesn't it? This is actually limestone, and that limestone is overlaying these really soft lake deposits. These are more siltstones. And so the limestone actually weathers slower, so it forms a protective cap on these. And that's why you have those hoodoos under there. All right, so that is your introduction to weathering. And next time, we're going to look at how to take those weathering products and put them back together and make a new rock.